Welcome to Mickey Study Circle channel. In this video, we shall see how to perform the stress analysis of a bar of constant area using the ANSYS APDL software. Moving on to the problem statement. So we have a simple steel bar of cross-sectional area 500 mm square with length equal to 900 mm and the Young's modulus being 2e5 Newton per mm square. So we need to determine the following parameters, that is the reaction force at the support, the nodal stress and also the deformation when the bar is subjected in the first case to a tensile load of 800 Newton and in the second case to a compressive load of 700 Newton. So we can assume the Poisson's ratio of zero point 0.3. So before we move on to solving this problem statement using the ANSYS APDL software, let us try to solve this using the strength of material approach. So first let us determine the values of the reaction force at the support. So you can just see that in case of the first case, that is the tensile load of P is equal to 800 newtons. So considering the sum of the reaction forces in the x direction to be equal to 0, we can just add up the forces. So that is the reaction force Rx, which is acting in the direction opposite to that of the tensile force Fx. So the sum of these two forces will be equal to 0, upon which we know the magnitude of Fx. Therefore, the reaction force in the x direction is yielded as 800 newtons with a negative sign. Moving on to the considering the compressive load of P equal to 700 newtons. So you can just see that the reaction force is acting in the direction of the compressive force and is opposite to it. So considering the sum of all the forces in the x direction to be equal to 0, we can just add up the parameters. Since the fx is acting towards the origin, so it is considered to be negative here. So the Rx yields the value of 700 Newton, which is positive. So this is about the reaction forces. In the next case, we shall take up the calculation of the deformation. So considering a tensile load of P is equal to 800 newtons, let us consider the deformation of the bar by the mathematical model given by delta L is equal to P into L by A into E, where P is the load acting on the member, L is the length of the bar, A is the cross section of the bar, and E is the Young's modulus. So P is 800 newtons here. The length of the bar is 900 mm and its cross-sectional area is 500 mm square. And the Young's modulus is 2e5 Newton per mm square. So upon substitution, we get the deformation of the bar to be equal to 7.2 into 10 to the power of minus 3 mm. So we can just see that on the application of a tensile load of 800 newtons, it is elongated by a distance of 7.2 into 10 to the power of minus 3 mm. Moving on to the second case, that is the compressive load of P is equal to 700 newtons. So using the same mathematical model for calculation of the delta L, we do get the value of delta L as minus 6.3 into 10 to the power of minus 3 mm. So we can just assume that the bar is getting compressed by a length of 6.3 into 10 to the power of minus 3 mm, which is indicated by the negative sign. Moving on to the calculation of the next parameter, that is the stress in the member. So upon the application of a tensile load of P is equal to 800 newtons, the stress induced in the bar is given by the mathematical formula, which is the ratio of the force acting on the member to its cross-sectional area. So here the value of P or F is equal to 800 newtons and the cross-sectional area is 500 mm square. Upon substitution, we get the value of the stress to be equal to 1.6 Newton per mm square. Similarly, with a compressive load of P is equal to 700 Newton, the stress induced in the bar is given by the mathematical model, which is again the ratio of the force acting on the member against its cross-sectional area. So we get the value of the compressive stress to be equal to 1.4 Newton per mm square, which is again can be considered as negative because it is the compressive stress which is induced in the bar. So these are the parameters that have been calculated using the strength of material approach. Now we shall see how the same problem statement can be solved using the ANSYS APDL. So we'll begin by selecting the preferences. Since it is only the forces acting on the bar without any considerations of the temperature. The problem is a structural domain problem. So select structural and click OK. Next is go for the preprocessor. Let us select a suitable element from the library. So click on add and select the element as link, that is given by 3D FINIT STN180. Click OK. So now you can just see that we have called the element link 180 from the ANSYS APDL library. Click close. Now we shall go for assigning the material properties. Select the material properties and select the material model and select structural, linear, elastic, and isotropic. So here we can feed the values of the Young's modulus, which is 2E5 Newton per mm square, and also the Poisson's ratio as zero point 0.3. Click OK. So you can just see that the material model is now changed to material model number 1. That means the link 180 is having the material properties defined under this section, that is material model number 1. So click close, and then let us go for defining the geometrical parameters. So click sections and select link and click on add. So let us just assign a number as 1. Click OK. So now you can just see that the link 180 has been assigned with the number as 1, and we can enter the link area to be equal to 500 mm square. So click OK. So now we have assigned the material properties, and in the sections we have taken the link as the element and defined the cross-sectional area for the link. Next we shall go for creating the model. So let us click on modeling, select create, and click on nodes, and let us create the nodes in the active coordinate system. So the first node is always the origin, so I'll leave all the x, y, and the z coordinates as 0. Click apply. The next node will be placed at the end, that is at a distance of 900 mm from the origin, which is nothing but the total length of the bar. So click OK. So you can just see that in the active coordinate system, we have got the two nodes, that is node 1 and 2. So now they need to be connected with an element. So let me go for elements and select auto numbered through nodes. Click 1 and 2, which are the nodes, and tell OK. So you can just see that the node 1 and 2 is connected by an element 1. So now we have defined the material properties. We have assigned the cross-sectional area to the link 180 element, and we have also created the geometry, that is by using the nodes 1 and 2 and connecting it by a element 1. So since we have already created the finite element model using the nodes, there is no need for us to go for meshing. So directly we'll go for application of the loads. So click on loads and select define loads and click on apply, select structural, displacement, and since the geometry is created using nodes, let us click on nodes. Select the node number 1, click OK, and arrest all the degrees of the freedom because the node 1 is fixed. So you can just enter the displacement value as 0 after having selected all DOF. So which is nothing but all degrees of freedom is having a constant value of 0. So click OK. So you can just see that this symbol indicates that the node 1 is arrested from all the degrees of freedom, that is both translational as well as rotational degrees of freedom. So now we need to apply the load which is acting at node 2. So first we shall consider the first case of tensile load with the magnitude of 700 newtons. So we'll enter the code by using the command prompt. So F indicates we are going to enter a force value, and node indicates the node number on which the force is acting. Similarly, the lab indicates the direction of the load, which is in the x direction given by Fx, and the value indicates the number or the magnitude of the load. So it is 800 newtons. So let me just click OK. So you can just see that at node 2 there is a load acting like this, which is given by the node 2. So now we'll go for solving this. So we have applied all the loads and the boundary conditions. Now let us go for solution. select solve and tell to solve the current load step file. So click OK and the solution is done. So click on close and close this window. Now let us go for extracting the results from the general post processor. So in the general post processor, first let us try to extract the reaction forces. So go for list results and select reaction solutions and select all items and click OK. So you can just see that the node 1 is where the reaction force, that is the support, is provided, and there the magnitude of this reaction force is minus 800 newtons. So click close after having recorded the value. So next go for the nodal solution and select the degree of freedom solution and select displacement vector sum and click OK. So now you can see that we have got the deformation at node 2, and at node 1 it is 0 because it is fixed, and at node 2 the value of the deformation is 0.72 into 10 to the power of minus 2. So this is what is the magnitude of the deformation. So the deformation is nothing but the elongation of the member, that is the bar. So click close after having recorded the value. So now we need to calculate or compute the stress that is present in the member. So for that, let us just go for the element solution and select the stress and select 1 measure stress, click OK. So we get the elemental stress at node 1 and at node 2 be equal to 1.6 megapascals or Newton per mm square. So this is the value of the elemental stress. So click close. So now we can also see how the stress could be calculated. So we'll go for plot results and select the deformed shape and select deformed shape plus and deformed, click OK. So you can just see this, the displacement is recorded here. So displacement in the x direction. So this white color line indicates the undeformed part of the bar and the blue portion indicates the deformed part of the bar, and this deformation is equal to 0.0072. So now let us use the element table to calculate the value of the stress. So click on element table, select define table, click on add, select by sequence number, select ls and assign the value of 1 and click OK and click close. And the element table, now let us go for element table. Select the items to be listed as ls1, click OK. So you can just see that we are getting the value of the stress in the element, which is equal to 1.6 megapascals or Newton per mm square. So this is one more way of extracting the values of the elemental stress. So next let us go for the plotting. So go for plot results, select contour plot, select element table, and here ls1 is already there, which we have defined previously. So select, click on s average, click OK. So you get the minimum and the maximum stress, which is equal to 1.6 megapascals. So this is the results that we have extracted, that is the stress, deformation, and also the reaction forces at the support. So now let us see how to extract the results of stress and deformation in multiple windows. So go for plot controls, select multi-window layout and select two, that is one at the top and one at the bottom, click OK. So now you can just see that the screen is divided into two equal halves. So right click on this window one and select the view. You can just see the isometric, so you can just see the isometric view of the bar. Go for plot controls and select view settings, or select style and select size and shape and tick the display of element to be on, click apply, click OK. So you can just see the 3D model of the component. So here again we can go for plot controls and select uh, multi-plot controls and select window 1 entity plots, click OK. So here let me select the deformed shape, click OK. Deform plus undeform, click OK. Now come here and select replot. So you can just see the deformation of the bar in the 3D view, in the isometric view also. So this is the deformation value, which is 0.0072. So similarly we'll come for the window 2 now. So go for plot controls, select multi-plot controls, select window 2 entity plots, click OK. Select element solution, click OK. And here we have defined the stress by sequence number, or just simply select stress, and in the x direction deform plus undeformed, click OK. Select replot, so you get the deformation. So in order to select the view, go for view and select isometric, so you get the isometric view of the component. So this is where the tensile stress has been acted and it has resulted in the deformation, as you can see here. So the maximum stress is 1.6 and the minimum stress is also 1.6. So this is how the stress distribution is seen in the member, and this is the distribution of the deformation on the member. So now go for plot controls, select write meta file, select invert white or black, and you can just save this as a JPEG image. So let me just rename this into 1D bar and save it in a particular folder. Now let us just try to open the folder and check the meta file, which is converted into the JPEG format. So this is how we can extract the results with a white background. So just go for file and click on save, and just save this as a PNG or JPEG format as per your convenience. So click on 1D bar, click save. So with this, we complete the ANSYS approach to determine the values of the deformation and the stress of a 1D bar subjected to a tensile load of magnitude 700 newtons. So the same steps can be applied in order to check the deformations and the stress of the bar of uniform cross-sectional area subjected to a compressive load of magnitude 800 newtons. Thank you all for watching.